Okay, hello, welcome everyone. Today it's a pleasure to have Horacio Casini from the Instituto Algebraic, who's going to tell us about entropic order parameters for the phases of QFT. So Horacio, please, the floor is yours.
Thank you, Ignacio. Thank you for the invitation to speak today. Well, this is the talk is about these two papers, these two recent papers done in collaboration with Marina Huerta, Javier Magán, and Diego Pontelo. And this is a brief plan of the talk. I will start describing the approach to quantum field theory based on operator algebras and regions, because it's the setup where the things can be thought better, especially the entropic quantities. And then I will talk about some simple properties of assignation of algebras to regions in quantum field theory that one can think they are like kind of axioms, and how these algebras and regions are related. And we will see that simple failures of these properties, additivity and duality, are related to symmetries. So this is the main topic of the talk. And one can see that the type of symmetry that one obtains depends on the topology of the region where these properties, additivity and duality, fail. When that happens, when one has this type of symmetries, then the net of algebras, so the assignation of algebras to regions, is not unique. One has more than one possible assignation of algebras to regions. And this leads us naturally to some entropic quantities that we can define, and we call it entropic order parameters that arise from this non-uniqueness, and somehow measure some order parameters related to these symmetries. It is interesting that these entropic order parameters satisfy some specific relation that we call a centrative relation that relates the statistics of dual entropic order parameters. I will explain this in more detail. And then at the end, I will just describe some heuristics of how these order parameters behave in different phases based on this idea of certainty relation. So let me start with this ideological, let's say, transparency. This is how information measures fit in quantum field theory. What is the role they play? So we have many formulations of quantum field theory. The most natural one is in terms of quantum fields, assigned to each point of space-time. And we know from the 50s that we can also obtain expectation values of products of these operators, and these give you numbers for the fields. And the description of the theory in terms of the quantum fields, or the description in terms of these expectation values, these Wigman functions, is equivalent. So one has the possibility to talk about functions instead of talking about operators. But there is also another old formulation of quantum field theory by Haag and Kastler in the '64 that is called Algebraic quantum field theory, which is based on not on just a field at the point, but on the full operator algebra in some region of space-time that is built up. One can think of polynomials of these fields, smear fields in some region. So the good thing of this approach is that it's some kind of a basis-independent formulation of the theory, because one can have, for example, different fields. We give the same algebra, for example, the scalar field, or the scalar field to the power of cube, or one can have dualities and represent the same algebra in terms of some basis of operators. But here we take all of operators in some region, and this is kind of basis-independent formulation. And in this formulation, if one would like to do the same step as here and produce numbers out of it, one can think a little bit about that, and given the vacuum state and the algebra, one can mainly produce some quantities that should be naturally entropic quantities, quantities that are related to the statistical properties of the vacuum state reduced to this algebra. So this is the way that, so one would like to give numbers to some algebra, and this naturally lead us to the entanglement entropy, mutual information, ranging entropies, etc., some entropic quantities that one can define. So let me start then describing what is the algebras, what are the regions, etc. The first thing is that the algebras attached to regions are von Neumann algebras. So these are just subalgebras of the full algebraic content of operators in a Hilbert space. And given a set of operators A here, one can produce a commutant, that is the set of operators in the Hilbert space that commutes with A. And automatically this A prime, I will call it A prime to the commutant, is an algebra. Even if A is not an algebra, could be not an algebra, this A prime is an algebra. And an algebra is always satisfies this relation, this von Neumann relation, that the algebra is equal to the double commutant of itself. So this is the definition of what is a von Neumann algebra. This is a very nice way to produce an algebra out of some operators. If we have some few operators, let's say, and one can ask how to close the algebra, doing products and linear combinations, well, the best way to do it is just taking the double commutant, and this gives you exactly what is generating. And for regions, we have some similar structure. We have some region in space-time, for example, this region V here, and then we can produce the commutant, so the causal complement. The causal complement is just the set of points in space-time, which is spatially separated from B. So this outside part, let's say. And again, we will call a causal region to a region like this W, this diamond here, which is equal to the double causal complement. So the complement is all this, and the complement of the complement is this diamond. So this region B will generate this diamond here doing the double causal complement. And it's natural to think that we have to assign algebras only to causal regions that are close like this, because if you have operators here in B, they will generate this operator O by the causal, the equations of motion. Let's say this O will be, you can express it in the Cauchy surface here by the causal equation of motion, or in other words, if you have the stress tensor in this region B, you can build up some smear stress tensor, energy operator, let's say, and push up the operators up inside the causal diamond. So this is not always the case, but we will assume that algebras are assigned to the algebra of B is equal to the algebra of the causal complement, let's say. So we only think in the causal complete regions or these causal regions. But then you have, yeah?
I'm sorry for the interruption, sir. By commutant, you mean it's any operation in the von Neumann algebra that we have defined for some QFT? A maps to A prime, which is the
no, sorry. Here this is not a map. This is A is some operator, some set of operators, and then A prime is just is not a mapping. Is A prime is just the set of operators we commute with all of operators in A.
Okay, I'm sorry. And is this commutation operation is with respect to the algebra that we have constructed? Meaning how we define the commutant depends on
you assume your operators have you know the product of operators.
Okay.
So you have, Okay, you have operators in Hilbert space, normal operators, bounded operators, let's say, in Hilbert space. So they have an internal product operation, and then just the commutant with respect to this product.
Yeah. Thank you, sir.
And then you can see here that there is kind of a pre-established relation. So this nice thing that the algebras are equal to the double commutant, and the causal regions are equal to the double causal complement, and you have the causal complement and the commutant, and there is also some relation between these two things because of causality, that things that are spatially separated have to commute in quantum field theory. So one could think how these things are related more precisely. And you can also see that there are more structure in these things. For example, the intersection of two regions is also the causal regions, is also a causal region. The intersection of two algebras is an algebra. And if you do the union of two causal regions, double commutant, double complement, let's say, is the smallest causal region that contains the two, and the same for the algebras. And this structure with some, let's say, least upper bound and supremum and infimum of two algebras, let's say, together with the causal complement form what is called an orthomodular lattice. And one could say, well, maybe there is a more profound relation between these two lattices, one of space-time regions, causal regions, and one of algebra. So what is the relation between algebras and regions? Well, the minimal requirements in a quantum field theory are these ones. One is that if you have a region that is smaller than is contained in another one, the algebra of operators should be contained in the other one. This is kind of ordering relation. This is natural because you think your operators are localized in the region, so it has to, if it's localized in a smaller region, it has to be localized also in the bigger region. And then there is also causality. That is what I have just said, that if you have an operator in a complementary region here, in a causally separated region, it has to commute with the operators inside this W. So these are the minimal relations, and one can think, given this structure, what would be the maximal possible harmony of these two structures. And one could think to call that a complete theory. A complete theory would be the one that satisfies all these relations. The first one is Haag duality, is called Haag duality. That is kind of enhancement of this relation. That gives you if you have the complementary region, you take the algebra operator in the complementary region and you do the commutant, it gives you the algebra of the region. So this would, in general, would be bigger than this one, but you can think maybe it's equal. And this other one is called additivity. Is just that if you have two regions and the operators in two regions, then the operators in the bigger region will be produced just by multiplying and taking linear combination of these two. So by the generated algebra of the two. And this is natural also to think this holds, because one can think the operators in a big region are locally produced by small operators. So it's kind of locality also this property. This other one is the intersection property, and you can think, you can see that this property just follows from these two. If they hold everywhere, this follows automatically. So I will not talk much about this intersection property. So these two relations are then things that one can think about and one can try to impose in a theory. They are proof, for example, for a free scalar. Of course, it's difficult to prove in general because you have to have explicitly the model, but it's natural to think as a starting point, and one can ask where these relations are violated in some specific models that are natural or that that are real models. And my talk will be about exactly that, how you violate these things. So let me then assume something, let us assume something which can also be violated by some other, like more non-trivial examples. But in general, we could think that for a trivial region, for a topologically trivial regions as a ball, we can impose that the theory satisfies duality and additivity. So we will assume that for topologically trivial regions there is no problems of additivity or duality. So, but that could be violated for topologically non-trivial regions. This is an assumption here. So suppose that this is the case, that you have a topological non-trivial region and something different happens there. So in this situation, you can define different algebras, and let me show how it happens. First, you take some topological non-trivial region R, and you can produce an algebra for R just by doing the union or the generated algebra of all algebras to all balls containing in R. So this is automatically additive, and this is called we will call it the additive algebra, the additive net. In fact, you can see that with this, you can assign algebras to all regions of space-time, and this is the minimal possible assignation of an algebra to a region, because as the balls are contained in R, the algebras have to be contained in the algebra of R. So this is the minimal possible net, and one can think, well, which is the maximal possible? The maximal possible algebra assigned to a region will be given by the minimal possible one assigned to the complementary region. So you take the minimal possible one to the complementary region, do the commutant, and this gives you the maximal algebra, compatible with causality, right? So in this situation, you could ask whether these two are equal or not. This is the question. This, of course, should be always bigger than this one, at least. And in the case that is not equal, it means that this maximal algebra, that is the commutant of the additive algebra corresponding to the complementary region, of course, contains the additive algebra of the same region, plus some other operators. These other operators, by definition, cannot be locally generated in the region R. So we could call it non-local operators in the region R. And the same will happen for the complementary region. The maximal algebra will be the additive algebra plus some non-local operators in the complementary region. So these operators are non-locally generated in these regions. So it means that in this case, when there are non-trivials A's and B's, we cannot have at the same time additivity and duality for the region R, because the region R prime at the same time, right? So these non-local, it's important to realize that these non-local operators are non-additively generated inside the topologically non-trivial region, but in general are locally generated in the theory, in a bigger region that is topologically trivial. So in a bigger ball containing R, these A operators will be locally generated. There is no problem in that sense. So there is nothing really non-local at the fundamental level in these theories. It's just non-locality with respect to some specific topological region R. So another consequence of this that you can see is that non-local operators come in pairs, somehow in dual pairs, because because one corresponding to the region R and one corresponds to the complementary region. And you can see that they cannot commute to each other. The A's and B's cannot commute to each other because otherwise you will have, the operators will be locally generated. Another consequence that these objects are algebras is that if you multiply operators here, it has to be represented in the same algebra, inside the same algebra. It means that these non-local operators should satisfy some kind of fusion relations. The product of non-local operators will be combinations of these non-local operators, and the same for the complementary regions. Of course, these n's in general can be elements, are not numbers, can be elements of the additive algebra here. But at least in the cases we have seen, you can always just find some particular non-local operators such that these are numbers. So let me give some examples. The first example is the case of global symmetries. You have a theory with a global symmetry, and we will see that this induces some problems, and algebra region problems for regions that have non-trivial homotopy group pi 0 or non-trivial homotopy group pi d minus 2. For example, the case of two balls have non-trivial pi 0 that counts, just this counts the number of connected components. And the complementary region is the outside part of the two balls have non-trivial p d minus 2. When I'm saying that the theory has global symmetry, I'm not meaning that this, for example, a free scalar has a symmetry under changing sign of the scalar, but this does not have any problem. The one that has algebra region problems is just taking the theory and making the orbifold of this theory with respect to the group of symmetries. It means that you take the algebra of operators that are uncharged with respect to the symmetry, that are neutral with respect to the symmetry, that are invariant with respect to the symmetry operators. You can think maybe this is kind of academic thing, but the fact is that every theory with a global symmetry, you can always produce this other theory. And also, this other theory is more like natural from the observational point of view, because in a laboratory, you cannot have an operator, for example, that violates the baryon number. All your operators will respect the baryon number. So really, the local algebras, the local operators that you can produce in the laboratory are these orbifold things. So let us see how these non-local operators appear in this case. You have the two balls, you have a charge operator here, and you have an operator here in the other region with the opposite charge. Both of them do not exist in the theory O, but the product of the two do exist in the theory O. They belong to the theory O, and this is called the intertwiner. This product is a neutral operator formed by a product of two charge and anti-charge operator. And you can see easily that this intertwiner does, even if it commutes with everything outside, the two balls will not be locally generated, because you cannot make it as a product of two operators that are neutral in the two balls. So this is a non-local operator in the two balls. And the complementary operator living in the outside part of the two balls is called the twist. The twist is just an operator that implements the symmetry group operation, but only in a region. Here I draw this dashed line, and inside this dashed line, this tau is producing the group symmetry operation, but not outside. So this operator, this twist, do not commute, of course, with the charge operator, because it produces a change in the charge operator. So it doesn't commute with the intertwiner, but it will commute with all neutral operators in the two balls, right? So you have the situation I have described before, in the sense that the non-local operators do not commute to each other, but they do commute with all other operators that are locally generated. So the twist will commute with locally generated operators in the two balls, and the intertwiner will commute with locally generated operators outside, because this twist is not locally generated in the outside part. In order to construct it, you need to go inside the ball and do something here. You can think, for example, exponentiating another current inside all this circle, and then you need operators inside to produce it. Well, in this particular case, you have fusion rules that are given by the fusion of the representations. These intertwiners are labeled by representations, and the twists are labeled by conjugacy classes of the group. And you have the group of fusion rules. And we have this structure that the commutant of the additive algebra of the two balls contains the additive algebra of the outside part plus the twist, because the twist commutes with the neutral operators in the ball, and the same for the outside part. The outside part, the additive algebra here, naturally commutes with the intertwiner. So the commutant will contain the intertwiner. So you see that this structure forbids that that you have duality and additivity at the same time. This is for regions with non-trivial pi 0, pi -2, but then you can think, well, what happens with regions which non-trivial pi 1. So, for example, this torus-like region in 4 dimensions will have a non-contractible circle. You can have a non-locally generated operator inside this torus, and then the outside part will have a non-contractible d-3 dimensional sphere, and you have a non-trivial p d-3. If you have non-local operators in this situation, you can prove that the algebra of non-local operators are formed by Abelian groups. So it simplifies and it's always an Abelian group. And the commutation relation between the non-local, you can label the A, for example, by representations of this group, and the B by elements of the group. So the A's and the B's are what is called dual groups, dual Abelian groups. One is the group and the other is the group of representations. And the commutation relation is just given by this simple relation, where this chi is just the character of the representation R evaluated in the element A. The way that you see that it has to be Abelian is because you can, inside your ring, you can produce this other kind of ring operator, but this, of course, is locally generated inside the ring. So it belongs to the trivial class, the class of the identity, but then you can fuse here using local operators and produce these two loop operators. And then the product of these two loop operators belongs to the trivial class. But when you have the situation that the tensor product of let's say a representation and the conjugate representation give you the identity, you have always an Abelian structure. It's an Abelian group. Well, this is more or less formal, but in gauge theories you can see this more transparently. You can think, well, what is non-local in a gauge theory inside the ring, and it should be something like a Wilson loop that is labeled by representations. But not all Wilson loops are non-locally generated. For example, if you have some charge operator with the representation R, then you can form this Wilson line, And this Wilson line will just give you a way to break this Wilson loop in pieces. You can have a Wilson line here, and a Wilson line here, and a Wilson line here. And in the product of this, in the algebra generated by this, you would obtain the Wilson loop. So the Wilson loop will be locally generated by product of Wilson lines ended up by the charge operators. And in a non-Abelian gauge theory, you always have these Wilson lines that are for the fundamental representation, for the adjoint representation. This F is the field strength. So you can always break the adjoint representation into pieces. So the adjoint representation is always locally generated, and of course all the products or all the representations generated by the adjoint are locally generated. So you get that if you go this way, you get that the only ones that are not locally generated are representations of the center of the group. So it's an Abelian group, the group formed by non-local operators. The dual operators living in the complementary region are called the Toff loops corresponding to the center of the gauge group. You can build up them as particular singular gauge transformations on a surface bounded by this B line here. But the elements, the group element that you use to do the gauge transformation has to be an element of the center in order that this surface operator does not depend on the position of the surface you use to produce the gauge transformation. So this gives us another way of producing violation of additivity and duality, but for different type of topologies. So in conclusion for this part, when a net of algebras does not satisfy duality and additivity, at least in the simplest way, then there are multiple choices of the nets. You can assign different algebras to the regions, and still the full operator content of the theory is the same. For example, here you can take away this A and take away this B from the algebras of these regions, and you have the additive algebras only. And this is a net does not satisfy duality, but still satisfy additivity. And you can enlarge then, you can see that you can enlarge the net by putting this A operator and not the B, because the B will not commute with A. Or otherwise you can put the B and not the A. And this gives you consistent nets which do not satisfy additivity. And you can, if you have many of these operators, you can choose in different ways the way to complete partially complete the algebras in such a way that duality is respected, but not additivity. When you take a maximal possible choice, then you end up with we call the Haag Dirac net, in the sense that this is related to the Dirac quantization condition. If you have, for example, in the Maxwell field, you can have let's say an electric flux here and a magnetic flux. In order that they commute to each other, they have to satisfy this Dirac quantization condition. That is just tell you that these characters here are the identity. So you have to choose the A's and B's that you are putting there in such a way that these characters are always identity. And it can be done in general in multiple. So the symmetries, these symmetries are encoded in the algebra for non-local operators. And the description of these things does not need a non-trivial topology of space-time, nor, for example, non-vacuum states, for example, charge states or superselection sectors. So you can describe it just by the structure of the net of algebras. If you go to other like homotopy groups for the non-trivial homotopy group for the regions, you will get higher generalized symmetries. So all the things that I have said somehow are the same that people have put some years ago in the terms of generalized symmetries associated to n-form gauge fields. But we obtain it here by just a different point of view. So let me then go to the entropic order parameters. The idea is that we can profit from the fact that there are more than one possible algebra assigned to the same region. So we want to obtain something that measures, for example, the expectation values of these non-local operators, or is related to the statistic of these non-local operators. So we are going to use the fact that we have, for example, here two algebras, one without the intertwiner and one with the intertwiner. So and we can measure the difference of the, let's say, entanglement entropies of these two algebras. But this is not well defined. We have to find out some way to define it properly. And for that, we have to use this idea of conditional expectation. The conditional expectation, now we have two algebras, one algebra M and one subalgebra N. So N is smaller than M. And the conditional expectation just maps the big algebra to the small one. And it's a positive map. It respects positivity of operators, and it's linear, and it also has the property that leaves all the elements of the small algebra in themselves. So if you have a conditional expectation of some product like this, where N1 and N2 belong to the small algebra, they can be put outside. The reason why this is interesting, this a special kind of maps called conditional expectation, is that they allow you to lift a state in the small algebra. If you have a state in the small algebra, this omega n, for example, is a state in the small algebra. Here I'm talking as a state for in this discussion is just a function of the operators that give you numbers. So I'm thinking this is a function that acts on the small algebra and give you numbers. And if I compose it with a conditional expectation, it gives me some function now that if you take an operator, an operator in the big algebra, epsilon goes to the small algebra, and this omega gives you a number. So the full thing will be an operator that now, an state now that in the big algebra. And the fact that this is a state is because this is a conditional expectation, so you can go through that. But in the present case, these conditional expectations are simply produced by the non-local operators themselves. So, for example, in this particular case, the conditional expectation is in this particular case, the big algebra is the two-ball algebra with the intertwiner, and the small algebra is the two-ball algebra without the intertwiner. And in order to go from the big algebra to the small one, you just average by the twist operator. The twist operator average over the group elements will kill the charge operator here and then kills the intertwiner. Well, and then the idea is that you have now then, because of you have the vacuum state, this omega now is the vacuum state, and the vacuum state composed with the conditional expectation is another state in the big algebra, in the algebra with the intertwiner. And then you can compare them using the most simple thing is the relative entropy between these two things. The relative entropy just measures how different two states are. And then secretly here is just measuring how much is the expectation value of this intertwiner. Because if the expectation value of the intertwiner is 0, it means that it cannot be distinguished, the vacuum state cannot be distinguished of this other state which just killed the intertwiner. So this is a kind of statistical measure of the expectation values of the intertwiner, but of course it's not a particular set of charge operators, but the full algebra here. So this will have information of the best intertwiner possible. And in a sense that I will not discuss, this is kind of a well-defined measure of the difference of entanglement entropies between the states with the intertwiner and without it. A bit more formally, what you have is this kind of a mathematical structure. You have let's say, the maximal algebra of the region R that contains the non-local operators. The conditional expectation takes you to the additive algebra, and the same structure for the complementary region. You have the maximal algebra for the complementary region R prime with the non-local operators, and there is a dual conditional expectation that takes you from that to the additive algebra for R prime. And in the vertical direction, what you have is the commutant. The commutant of this algebra is the additive algebra of the complement, and the commutant of this algebra is the additive algebra in the region R. Once you have this structure, it's interesting that the relative entropy order parameter, let's say, that one assigned it to the region R through this conditional expectation, and one assigned it to the region R prime, the complementary region with this conditional expectation. If you sum the two, it always give you some specific number. In this case, it's just the logarithm of the size of the symmetry group. So this relates these two order parameters, of course, for complementary region, not for the same region. Well, this property, we call it entropic certainty relation in our paper of last year. This is another paper by Javier Magan and Diego Pontello, where they prove it more generally for finite dimensional algebras. And then we realized that there was a previous, like a mathematical oriented paper where they proved something like that also in the context of type 3 algebra in quantum field theory, but thinking more in conformal field theories in 2 dimensions. And there is also this very recent paper by Holland. So now this is completely proved at the full level of rigor in quantum field theory. So let me say why we call it entropic certainty relation. What does it mean? Well, we call it certainty because it's an equality, but it has a lot of relation with uncertainty relation, normal uncertainty relations in quantum mechanics. One can see the following. For example, because the relative entropy is always positive, it means that this order parameter is always smaller than log G. And this other one, for the complementary region, is also always smaller than log G. So it's between 0 and log G. But of course, this relation tells us that they cannot both saturate at the same time. They cannot both go to log G at the same time. If one is large, the other will be small. And this is the same type of things you obtain from the uncertainty relations for operators that do not commute to each other. These A's here and these B's here do not commute to each other. So this Wilson loop, let's say, and this Toff loop do not commute to each other. So they cannot both go to maximal expectation value at the same time. And but the interesting thing is that if you take not just the Wilson loop and the Toff loop, but the full algebra, you get an equality here. This is somehow related to the idea of that the entropy of a region in a pure state is equal to the entropy of the complementary region. a bit of the heuristics of this order parameter is as follows. If you suppose you have, for example, again, these two balls with the intertwiner, and suppose for example, you would like to know when this order parameter goes to 0. Well, it goes to 0 when the intertwiner has very small expectation value, for example, when the balls are very far apart. Because in that case, the conditional expectation do nothing to the vacuum. It just kills the intertwiner, but the intertwiner has also expectation value 0. So, so these two states are the same, and the relative entropy goes to 0. Otherwise, for the complementary region, instead, the twist operator now, the best twist operator is very spread, very like a smear. So it looks like a normal, like a group operator in the full space, let's say in the limit. And then it has expectation value going to 1. And then this order parameter go to a maximal value. Possible the difference between these two states is maximal and goes to log G. And on the contrary, if you take the two balls very near to each other, this twist operator will be squeezed and have 0 expectation value, while the intertwiner, you can place it very near the boundaries, such a way that the intertwiner has maximal expectation value and you get the opposite relation. This same relation, the entropic certainty relation, if you can use it using monotonicity of relative entropy to put, for example, if you are interested in this order parameter, you can have a handle on how to compute this order parameter by putting lower and upper bounds using this relation. A lower bound will be the relative entropy in any smaller algebra than this one. For example, if you restrict attention to the algebra generated just by the non-local operators, if you have a set of non-local operators whose algebra close in itself, you can evaluate the relative entropy in that. And this depends only on the expectation values of these non-local operators, and you can put a lower bound to this. And putting a lower bound to the complementary region in the same way, you can put an upper bound now to this order parameter. That depends on the expectation values of the complementary operators, the other operators. For example, with this, you can compute in the simplest case. For example, this is for the Maxwell field in a ring-like region. And we have chosen here an algebra that contains some Wilson loops which have charges multiple of some number Q. And then you can take, for example, the algebra of some Wilson loops, which are exponentials of the free field, and then maximize doing maximization for the smearing function that you use, and then give you a lower bound, and the same for the complementary region, and then you get these curves here that describe how the order parameter behaves with the ratio between the width and the radius. And you can see here are some formulas. You can see that when the ring is very thin, the relative entropy goes exponentially to 0, exponentially fast to 0 in the length of the ring. This is a perimeter law, let's say. This is a perimeter law, and you can compute more or less accurately the coefficient there. And in the opposite case, when the ring is very wide, because in this case, of course, the group is infinitely dimensional, so you don't have log G, you have infinite there, so it's unbounded. When the group is, when the ring is very wide, it doesn't have a bound, it increases forever logarithmically. And you can see that the upper and lower bound differ only by a constant here. The logarithmic part is the same, and the constant just is bounded between these two very near numbers. So this is just less than a bit, let's say. So this is like a digression like, so I will not explain it in detail. So it's just, this is very well known, that is a paper by Bachas in the 86, that using reflection positivity of operators, you can prove that any operator, any type of Wilson loop operator that you have, expectation value, you can write as exponential of some potential, and this potential, because of concavity properties given by reflection positivity, this potential is bounded between a kind of perimeter law and an area law. So in particular, you can prove that it cannot decay faster than the area, right? But this is general. This does not take into account if you have a locally generated or non-locally generated operator. But if your operators are locally generated, you can do something like this. Use again, so you can start building up your operator by pieces, and using reflection positivity again, you can prove that the potential is bounded, cannot decay faster. So the expectation value of the Wilson loop cannot decay faster than the perimeter. That is what we know. For example, for QCD, the Wilson loop cannot decay as an area because you have quarks, it's locally generated. So it means that if you have for example, an order parameter for confinement, that you expect to have an area law, you must have automatically a non-local generated operator. So, and with that, you have automatically several possible assignations of algebras to ring-like regions. So order parameters with area law imply that you have more than one possible algebra, and then you can also have these entropic order parameters. That do not depend, the interesting thing of this entropic order parameter is that they only depend on the geometry. You don't have to pick up any particular like non-local operator inside. They just are a function of the vacuum state and the geometry. So you can go to compute these things in different scenarios, or to put bounds in different scenarios, and you can restate the usual law about order parameters in terms of these relative entropies. And then you find something similar. You find that the relative entropy obtained by killing the Wilson loops is exponentially small with the area in the case of confinement, and the one of the top loops goes to a constant as you increase the size of the ring. And in the Higgs phase, you have the opposite situation. In the conformal case, you expect that both of these order parameters go like the perimeter. So here we have like a kind of digression with respect to the literature, because in the literature, people have also thought about if you have a perimeter law, you can somehow like, because your expectation value goes like a perimeter, you can somehow renormalize your operator in such a way that it goes like a constant. But we can see here that this cannot be done arbitrarily in our case, because we want our operators to satisfy group laws. So we cannot just normalize arbitrarily the operator. And then you can see that this case, conformal case, cannot be really renormalized to a constant law. While in these cases you can, but here normalization means that you increase the width of the loop if your ring is wide enough to cross the scale of, for example, of the symmetry breaking, then the Wilson loop will go to a constant law. And here is another commentary about the conformal case. Because of the certainty relation, you can see that some particular relative entropies here is a relative entropy. In four dimensions, you have non-local operators, the Wilson loop and the Hooft loop, live in the same ring. They both have the same topology and they can live in the same ring. So you can have a relative entropy that kills both. And this, because of the certainty relation, satisfies a relation that relates the relative entropy in some ring with a specific, so you can describe these rings in the conformal case by some cross ratio, and you can see that the outside part is conformally equivalent to a ring like this with a different conformal cross ratio. But there is a point where these two complementary rings have the same cross ratio. And in this case, you can exactly fix the value of this relative entropy to be the logarithm of the size of the center of the group. And this perhaps we naively, but perhaps for us is like very strange or very particular, because, for example, in these super-Yang-Mills theories, you have a tunable parameter, the charge, so the coupling constant, and the theory is still conformal if you move the coupling constant, and this should change the expectation values of these non-local operators, but in this particular case is fixed to a specific number. We cannot, of course, compute this for other cross ratios. So, and this is a kind of a heuristic idea on how these two laws, the constant law and the area law, appear naturally in this context of these relative entropies. And the reason is the following. Suppose you have, you want to understand how some order parameter, say a Wilson loop here, goes with the size of this loop as you increase the size. Then you can think putting in the complementary region Hooft loops in some black rings here, and then if you suppose that there are few correlations between these Hooft loops, you can put many of them, and you can use the equations to see how the relative entropy in the complementary region can get a lower bound using many of these rings that you assume that are uncoupled. If you do that, you can see that this relative entropy will go exponentially to the saturation, with the number of these black rings that you put that have to be independent, and the number of independent loops that you can put is dictated by the area of this orange ring. So naturally, it gives you, because of this certainty relation, it gives you a bound on the entropic order parameter for the orange region, which goes exponentially to 0, exponentially in the area enclosed by the ring. So this is how this constant law, let's say the constant law is the law of these black rings, and the area law of the orange ring are related in this context. So if you have instead a perimeter law for the black rings, this cannot be used to put an area law for the orange ring, because when you increase the size, the expectation value of these black rings will go very fast to 0, and it will not help you. You can only just put small rings around, and it will give you only a perimeter law for the orange ring. So one thing that these ideas bring in mind is that people have along the years thought much about these subjects, but perhaps not much about smear Wilson loops, or smear, let's say, Hooft loops, in the sense that operators that have some width, people have thought much about operators that are line operators, just a line, because are simple to describe. So you have a line operator with, let's say, the limit of 0 width and some length, But in this context, it's natural to think of different geometries, in particular wide rings. And then you can think, well, what happens with this idea of confinement or symmetry breaking if you enlarge your set of operators to ones that can have some width? And then the natural idea is that you are thinking in what happens along the normalization group flow. So the natural idea is to think in scaling regions. So to take some ring, we have some geometry, any geometry, and scale it homogeneously, going to the infrared. And if you think in this situation, then the terminology of what you expect is much simpler, because what you expect is that, for example, in the confinement or Higgs phase, one of the order parameters go to 0. For example, if you have an area law, it will go to 0, and the complementary one will go to the maximal possible value. What is the same as to say that there are fat operators here, fat Wilson loop operators with expectation value going to 0, and fat top loop operators with expectation value going to the maximal 1. They say 1 is expectation value of a unitary operator that goes to 1. And in the Higgs phase, you have the complementary thing, the converse. But an interesting point is that these things should be saturated, so these expectation values or a relative entropy will be saturated independently of the shape of the thing as you increase the size. While in the conformal case, both will depend on the cross ratio, let's say, will depend on the original geometry. And as you have saturation here, this gives you the idea that you can check that as the expectation value of these fat operators are saturated to 0 or to 1, what happens is that the correlations between these non-local operators are 0. So you have, for example, a top loop with expectation value 1, and you take another one separated of it, it will have all correlation functions, connected correlation 0. So it's somehow these scenarios are related to the idea of a gap or 0 correlation, at least for the non-local operators. Of course, we would like in this context to understand how to have a handle on how these order parameters behave as you increase the size of the region. This will give us, for example, understanding what happens with the order parameter for small rings in a asymptotically free theory. Will give us a handle to determine if in the infrared will have a confinement or whatever. But of course, we don't have this handle up to now, but it will be nice to have one. So I just end with some brief commentaries. So this investigation somehow remarks the importance of wide loops to understand what happens with wide loops. Already this certainty seems to point to some instability in the relation between ultraviolet and infrared. You can see that suppose you have a situation that ultraviolet for small rings, you have somehow Wilson loops and top loops that have similar behavior. Once one of them start dominating as you increase the size, then it will produce that the other one it goes to a smaller value. So somehow there is something like, at least naively, something like, because of this idea, something like instability of the asymmetry between the complementary operators, the dual operators. Well, one would like to compute these order parameters in the weak coupling regime for non-abelian theories. We haven't done that. And there is also a more like formal question, how to generalize these things to other topological features of the regions that are not just the homotopy groups. Okay, thank you. I have finished.
All right, thank you very much, Horacio. We have time for questions. Michael, do you have a question?
No, sorry. I mean, I put like the claps, but there's a question from Carla actually.
Horacio, hello.
Yes.
A question. So can you go back to that transparency where you explain? So you talked about your entropic order parameter, and you said it goes in the confining case as area law. I think it's the previous, yeah, that one. So this.
This one.
No. Next. I think that. Yeah.
There's this one.
No. We have a delay. The one that has the Wilson area law and the perimeter law for the Hooft, etc. And then you said,
one.
Yeah. This.
Yeah. Okay.
Then you made one. You made one comment about the conformal case in contrast with these ones. So I agree with all these laws you write here. This is what the entropic order parameter do.
Yeah.
But I didn't understand. You made one comment that I didn't write it about the conformal case in contrast.
Perhaps perhaps the comment that you are mentioning is the one about what people said about that you have the constant. So people say that you have traditionally one thinks of area laws or perimeter laws, right? But people say that if you have a perimeter law, you can think the expectation value in that case as a constant, in fact, because you can somehow renormalize the operator locally along the line in such a way that to eliminate this perimeter law and give you a constant, right? This is a commentary that you are.
Yeah.
Well, what I say is that we have some kind of qualification of that commentary in this context, because in the conformal case, there is no way you can renormalize really in order to have a constant here. You can multiply by something, okay, but still your order parameter here it will be perimeter law. And also for the operator or the parameter, suppose you have an operator that is a kind of Wilson loop, we have a perimeter law. You cannot renormalize it in such a way that it is still unitary and still satisfy the group operation and has a constant law. In that case, you cannot do that also for the case of confinement or Higgs phase. The way you get a constant law is just by increasing the width. By increasing the width and crossing the scale of the gap, for example, here, then you see that the Wilson loop will have a constant law, but only once you have a sufficiently width loop.
Okay.
So it's a fat loop.
Okay.
And in fact, even if you have a fat loop with a size of width bigger than the scale of symmetry breaking, and you keep this size fixed and increase just the length of the loop, if the length of the loop is large enough, still you have a perimeter law. So this is what is said here. So for exponentially large loop, but with a width fixed, you cannot get away from a perimeter law. You will get a perimeter law still, but of course it doesn't matter much because it's a perimeter law for very large loops. Right?
Okay.
So in that sense, what I was saying precisely here was that thinking in terms of really of order parameter for just entropic or operator order parameters, but for wider regions. So in the operator case, it will be an operator attached to something with here, so some smear thing. The terminology simplifies enormously because it's only this that you get. While here you have to do, well, I would like to have a constant law because otherwise I cannot have area law here. The certainty relation prohibits you have a perimeter law and area law. You have to have something like this. But in order to say that I have a constant law, I have to say, well, I have enough width, and I have to have enough width, but not that large the length and whatever. So, I mean, the terminology of the line operators is somehow cumbersome because precisely in order to describe romanization group, because precisely the line operators are not ultraviolet and not infrared, are in the middle. You have one size that is small and one size that is large,
okay,
right? So they are in the middle, while if you just increase the whole thing, you are really going to the infrared here. So it's just it doesn't mean it has something new. But I think it's a good point of view to open to different things.
Can you think of a holographic way of calculating the entropic parameter?
Well, we are thinking of that, but in fact, it's interesting your question because in holography, for example, the most well-known thing is these super Jamils n=4 that are conformal and that, in fact, are theories that, in principle, they have these symmetries because you don't have fields in the fundamental, right?
Yeah.
So it means that in the bulk, or it means that you have at least several algebras that can be assigned to a ring, right? And then it means that you can have in the bulk something related to the entropies of the rings that has a correction depending on what algebra you choose. And this correction will go like log of G. In this case, it's log n. It's log n. So it means that it's a correction to the entropy that is not captured by Ryu-Takayanagi because it's n squared, but it's not also order 1. It's not all order 1 as a single field, let's say, in the bulk. So it's order log n. Of course, one could think it should be given by these Wilson loops with the string attached, etc. But I do not know if people have thought about, for example, to compute that, how to smear a string in the bulk. So if you have a wide Wilson loop in the bulk, in the boundary, how do you compute this expectation value in the bulk? Yeah. That would be the way to understand this contribution to the entropy in the holographic case, I think.
Yeah, okay. Maybe one should not calculate it with a string, right? But with an extended object that by itself has.
Yeah, okay.
A width.
Yeah, exactly. I don't know. An extended object that it would be like a smearing of a string. That is
no. It's not the same. Indeed, it's not the same. But okay, yeah, good to think. Yeah, good to think. Good thing to think.
Okay.
Yeah. Thank you. Thank you very much.
Yeah.
Are there more questions? Carlos?
Say one more, Horacio. In the beginning, you made this comment of the Wilson loop that you can break by putting the quarks, right?
Yes.
Yep. It was in the very beginning. Yeah. Was the whilst if you put it in the fundamental, you put F mu news and you generate sort of a Wilson line, etc. Yeah, exactly there. But then you said something about that the operators you wanted, they should be sort of gauge. They should not be charged under a flavor-like symmetry, right? And this you commented in the context of the orbifold of probably the next transparency or the next.
Okay. Well, what I said is that in order to describe the things for the global symmetry, so this is something that happens only for the global symmetry. For the other things, I don't have this problem because exactly we do not know how to invent. So in this situation, our theories are automatically like this O. You don't have a way to invent this F, the full theory. So there is a theorem by this DHR theory that tells you that if you have this orbifold kind of algebras with all this stuff, you can always find another theory that is this F theory, which has charge operators in such a way that this F theory doesn't have algebra region problem, and you can form the O theory by just making the equation, the ratio with respect to the group. So, but this structure does not exist in higher generalized symmetries, in the sense that we do not, somehow, in order to do that, one would allow for, let's say, gauge non-invariant objects or something like that.
Yeah.
And this will conflict with the positivity, etc.
Yeah. Okay.
So this is a particular thing. So in some sense, the ladder goes to these generalized symmetries here, and then if you go to the case of pi 0, then you get to these orbifolds. And the other one is kind of an accident of these particular theories, I would say. So there is a way to invent another theory that is complete and doesn't have problems, and still you don't need to put for completing the theory. You don't need to put additional information. All expectation values are already here in the back. For example, the expectation value of the charge operator is 0, but this one is already no, right? So there is no new information for the theory F. You get it from O.
Okay.
And here, of course, in these theories, you can complete them. But you can put, for example, for this non-local operator, you can put a charge. But you already changed the expectation value. You already changed your Hamiltonian and everything. So it's not the same thing.
Thank you, Horacio.
Okay.
Okay, if there's no further questions, we thank Horacio again.